Good evening. Thank you all for coming tonight. Welcome to our 6th presidential lecture in chemistry. First of all, I'd like to thank President Joffrey for making this possible. President Joffrey is here in the audience tonight. It's extremely important for us to have the seminar series. No university can claim to be great or even good if it doesn't have a strong, vibrant seminar series to inspire students, to stimulate its faculty, and to educate the general public. And it's very important to have this, and again, I thank President Joffrey for making this possible. So at this time, I'd like to invite Professor John Vercade, University Professor in Chemistry, to come to the podium and introduce tonight's speaker.
Thank you, Jake. It is indeed an honor to introduce our 2011 presidential lecturer, Professor Richard Royce Schrock, Nobel laureate. Now, I believe our speaker's parents might have known something when they named Richard Royce Schrock, because they named him most appropriately. Richard comes from Old German, meaning powerful leader. Royce comes from Old German, meaning famous. And Schrock is the name of a place near Marburg, Germany, called Schrock, except they put an umlaut over the O, and it becomes Schrock. So he would be known as a powerful and famous leader in chemistry from Schrock. Now, Professor Schrock was born in 1945 in Bern, a small farming community in northeast Indiana. For Professor Schrock's 8th birthday, he received a chemistry set from his older brother Theodore. And since young Richard was very learned in the area of carpentry, which he learned from his father, who was a carpenter for his trade, Richard constructed in a room in his house a small laboratory, which also had a lot of shelving for his growing collection of test tubes and flasks and beakers. Now, Richard really liked testing recipes for mixtures of various kinds, including fiery ones, but only once was it necessary to call the local fire department to put out a fire from one of those fiery experiments. Now, in his address tonight, Professor Schrock may elaborate on the circumstances surrounding that fiery experiment, and he may not, I don't know. In 1958, his family moved to California, and in 1967, he received his BA degree from the University of California at Riverside. Then he went to Harvard, where he received his PhD in 1971 with John Osborne. And then he went to Cambridge. Now, that's not Cambridge, Iowa, that's Cambridge in England, for a year, funded by a very prestigious National Science Foundation postdoctoral fellowship. And he went to work with Sir Jack Lewis. Professor Schrock then took a job at DuPont's Central Research Department in the days when they used to do a lot of academic and fundamental research. During a scientifically very creative and fruitful 3-year stint at DuPont, Professor Schrock's extraordinary research prowess became a subject of some attention by Barry Sharpless, who was a professor of chemistry at MIT at the time. And in fact, as a result of that interaction, Professor Schrock received an invitation to join the chemistry department at MIT in 1975. And at MIT, he was promoted to full professor in only 5 years. In 1989, he became the Frederick G. Keyes Professor of Chemistry. In 2005, Professor Schrock won the Nobel Prize in Chemistry, which he generously shared with Yves Chauvin of the French Petroleum Institute and with Bob Grubbs at Caltech. In addition to the Nobel Prize, Professor Schrock has won many other prizes, awards, and honors. And I'll mention only a few. An Alexander von Humboldt Award in 1995, the American Chemical Society Award in Inorganic Chemistry in 1996, the Baylor Medal in 1998, and the Cope Scholar Award in 2001, the Sir Geoffrey Wilkinson Lectureship and Medal in 2002, the Sir Edward Franklin Prize Lectureship in 2004, and the F. Albert Cotton Award in Synthetic Inorganic Chemistry in 2006. He's an elected member of the American Academy of Arts and Sciences and also a member of the National Academy of Sciences. He was associate editor for the journal called Organometallics, published by the American Chemical Society, and that was for 8 years. He has published over 500 research publications. Now, in the metric system, that's 500 milligilmans, because Professor Gilman had over 1,000 publications throughout the course of his career. However, I'm sure Professor Schrock's career is by no means over yet. Now, Professor Schrock has many research accomplishments, and I'm only going to mention one, besides the fire in his house. A goal of chemists for the past half a century at least has been the achievement of a cheap and efficient way to make ammonia simply from atmospheric nitrogen and hydrogen. And that's not a very cheap process to do at the present time, but in 2003, Professor Schrock made an astonishingly large step toward that goal. And he did that by demonstrating for the first time that by building a carefully constructed molybdenum compound as a catalyst, atmospheric nitrogen gas could be converted to ammonia in good efficiency and yield by using hydrogen ions, very simple ions, and electrons. And that was occurring for him in his laboratory under very mild conditions, atmospheric pressure and room temperature. Now, in nature, certain bacterial enzymes in the soil convert nitrogen compounds to ammonia. And Professor Schrock's results suggest that a single molybdenum center in nitrogenase enzymes may be the catalytic site at which nature performs that marvelous reaction of converting nitrogen to ammonia. And of course, ammonia is, as we all know, a primary fertilizer for farm crops. Professor Schrock, Professor Joffre, and Professor Pettridge, would you join me at the podium here for presentation to Professor Schrock, the commemorative plaque of his presidential lecture, which is entitled A Lifetime of Chemistry, Reflections of a Nobel Laureate. And by the way, Richard, the check is probably in the mail.
Okay. Thank you. You want us to come around here?
Yeah, come on around this side.
Okay. Thank you very much. Thank you. Is this working? Yeah, it seems to be working. You hear me back there? Okay. Thank you very much for those wonderful comments, John. It's a nice outline of my talk, or at least the personal side of it, that I'm going to talk about in the beginning here. And it's a great pleasure. I've known Professor Joffre for a number of years. great inorganic chemist. I asked him if he does any chemistry anymore. He says occasionally he thinks about it, but he has other problems. I know that. So this is a public talk, as you well know, so it'll be a little light on the chemistry. Tomorrow will be a technical talk, which will be a little heavy on the chemistry, light on the other things. I hesitate to show this first picture because my mother hated it, and but it gives me some pleasure to show you where I came from, and it's an interesting one. That's Decatur, Indiana. So I was born in Bern, and Decatur's about 13 miles south of Bern, and my parents left Bern when I was born, not because I was born, but for other reasons that I won't go into, and moved to Decatur, and that's where I grew up until I was 14 or so. And since that's the summer of 46, this is me right there. And that's Ted, my 5-year older brother. He's the one who gave me the chemistry set. And this is Luther, 10 years older, my mother and father. And my mom hated this picture because she said it made us look poor. And, well, we weren't poor, but we weren't rich either. So, as John said, I moved to California when I was 14 and went to Mission Bay High School. I was there for half a year in junior high school. And I continued my science that I told you a little bit about. This is a contest, a science contest in San Diego that I won some prize for. You can see there, for the effects of osmosis on sea urchin eggs. I went out and got the sea urchins myself, cut them up, got the eggs, and did all the work, and appeared in a newspaper there doing my work. That you can't see the date, but that says February 1961. So I was a junior in high school at that time. And so I continued my science through high school. I never thought I would do anything but continue my interest in chemistry. And I went to Riverside, learned a lot at Riverside. I worked for a man named James Pitts, who was an atmospheric chemist. I did a lot of infrared studies of what was in the atmosphere as we knew it back then. I built a vacuum line, learned how to glass blow, and really learned a lot. And that was my first summer in 1968, that would have been, and I studied for every year and every summer thereafter before I went to Harvard. Here's a picture of me. You can't see it maybe, but I'm smoking a pipe. And I thought it would make me smarter, but it really didn't have much effect. So I stopped doing that a number of years ago. But I thought it was cool at the time. So at Harvard, as John mentioned, I worked for John Osborne. And I don't know if you can see that picture. Maybe is it possible to dim any of the lights up front here? Can you get these guys up here? That's good. Maybe that'll help. So this is a group. That's John Osborne at the end. That's Dave Rice. Yeah, and here I am with my hand on his head, blessing him, I think. So that was the group at the time. We had a great deal of fun. John was a good friend my whole life. And as I mentioned at the end, he passed away 11 years ago now of brain cancer at the age of 60. One other thing I did when I was at Harvard is I met my wife, Nancy, and this is a rather interesting picture. You can see a rather long-haired guy, and she's a kind of a flower child, and that's the way it was back then. In 1969, I met her, married her in 1971, just before I went to Cambridge, England, to do a postdoc. Here we are coming back from Cambridge, England. I'm all natty in my sweater and everything, and we bought a couple of bicycles. Hers has been sacrificed for my son, and mine I still have and ride, believe it or not. I mean, it's not a great bike, but, you know, it's a bike. And I think they were 67 pounds apiece, which was about $150 at the time. Then I went to DuPont. As John mentioned, in 1971, there were no jobs. That's why I went to England as a postdoc. 1972, the situation wasn't much better. but I managed to meet a guy named Earl Muterdes in Cambridge, and Earl Muterdes was one of the 6 associate directors at DuPont. Oh, I can move around? Oh, good. Yeah, thank you very much. Earl Muterdes is one of the associate directors at DuPont, and he sort of interviewed me, and he said, well, do you want a job? And I said, sure. So I took that job at DuPont, which was, as John mentioned, a real research department. And that's when you could do what you wanted there for 3 years or so before you had to do something useful. But sometimes what you tried to do turned out to work. And what DuPont did at the time, and still does, is, of course, make polymers. And so my charge was to make some new polymerization catalyst. So I learned about catalysts from John Osborne. I studied some rhodium chemistry and rhodium in this periodic table, which I assume you all know by heart. Rhodium is right here in group 9. And over here is in the what we call the early metals, group 4 and 5, is titanium, which would make polymers, and vanadium, zirconium, and chromium, things like polyethylene, polypropylene. And so my proposal, it was a very simple proposal to my group leader, George Parshall, was to study the organometallic chemistry of tantalum down here. So nobody had done that. At least I didn't know of anybody having done that. I found out later, fortunately, that somebody had begun that. That's really what started me on my research career, and I'll tell you about that. And then I'm highlighting right next door in group 6, molybdenum, element 42. That's the answer to life, the universe, and everything. And tungsten right below it. So these are the elements, along with rhenium a little bit, that have really comprised what my career is all about. And then this is the question for the scientists in the audience. Anybody recognize who that is? That was, he joined, this was as a graduate student at Indiana University. He was my lab mate at DuPont. A guy named Fred Tebbe. That's Fred Tebbe, entering graduate school at Indiana University. He passed away in 1996 of pancreatic cancer. He was a heavy smoker and didn't bother about benzene and such. And I don't know whether they had that effect, but that's a fact. So, yeah, that's a picture of Fred Tebbe. He was a great chemist, and I learned a lot from him. I learned a lot about metal-carbon bonds. Metal-carbon bonds. That's what organometallic chemistry is all about, which is more or less what I've done my whole life. So Fred was my lab mate. Jeff Wilkinson, who received a Nobel Prize in '73, was a consultant. They still had consultants at places like DuPont back then, and so these great men would come through, and you'd get a chance to sit down with them and tell them what you were doing. And I did that, or actually I went to a lecture where he talked about this compound here. So this is tungsten. This is that metal at the bottom of group 6. And it has the possibility of putting 6 things around it, 6 anions, as we call them, these methyl groups. So these are 6 methyl groups around tungsten. He showed that he could make that. He did make it. He characterized it in 1973. The summer of 1973 was when he gave that talk, or maybe it was a little earlier in the spring, to us at DuPont. I thought that was wonderful. I was beavering away in tantalum chemistry, but I could put 2 and 2 together. I figured, well, if tungsten's in group 6 and tantalum's in group 5, maybe I should put 5 of those methyl groups around tantalum. That would be a good thing to do. Maybe I'll went ahead, yeah. Well, we're going to run through a lot of these. I can see that. I'll go back to this one. All right. So that's what I tried to do. Jeff Wilkinson, in his Nobel address, you have to give a talk when you get a Nobel Prize, and he said down below here, pentamethyl tantalum, R. Schrock, DuPont, Wilmington, Private Communication, has recently been synthesized, because he had written about hexamethyl tungsten in the Nobel address. I think he's still working on it. So that's what I tried to do. And fortunately, this man, Juvenol. I don't think this is... I didn't think you make me work so hard. You got another one?
Yeah, we'll trade you here.
Is this one working? Ah, thank you. So a man named Juvenal, somebody I've never heard of since and didn't know at the time, who was at the Jet Propulsion Laboratory in Pasadena, for some reason, had made trimethyl tantalum dichloride. So all I had to do is replace two methyl groups or two chlorides here, CO minus groups with methyl groups, and make pentamethyl tantalum. I show one of them expanded here. Carbon has 4 things bound to it, 1 bond to the metal and 3 bonds to H's. And that's what I did. It, however, unlike hexamethyl tungsten, was quite unstable and decomposed above where ice melts at 0 degrees. It decomposed in what was called a bimolecular fashion. So 2 of these molecules, well, there's a whole bunch of them, but they would collide with each other and decompose in a way I won't go into detail about, which I studied. But in order to prevent that bimolecular decomposition, I just put a big other group in place of one of these H's. I put another carbon with 3 methyls on it. So this is called neopentyl, pent for 5. Neo is the shape of this ligand. And I tried to make pentaneopentyl tantalum. So that seems like a logical sort of thing to do. And I was having fun. I didn't have to make polymers, at least in my first 3 years. And I tried to do that, and fortunately it failed. Now, I say that because a lot of things are fortunate to fail because you find that you make a discovery. So this is the eureka moment. When I tried to make this pentaneopentyl tantalum, which probably is an intermediate in the reaction, what happened is it decomposed intramolecularly. It didn't run into another molecule. It's too big and bulky. But one of these neopentals took an H from a neighboring neopentyl and made what we call a neopentane, and then created a carbon-metal double bond. So there's still 4 bonds to carbon, now a double bond to the metal. This was a new type of compound for various reasons. It's called a high oxidation state alkylidine or carbene complex, and that was published in 1974. This is an unusual compound because it has these big bulky groups on it. It's very stable towards this bimolecular decomposition, and in fact you can distill it like you would water at a low pressure and a temperature of about 75 degrees. Very, very surprising for a brand new, exciting compound like this. Well, why do I tell you this? Because the double bond, the metal-carbon double bond, is a very important feature of everything I do these days, and this was where it all started. And because there was a lot of talk in the air about a new reaction that had been discovered at DuPont, curiously enough, in about 1956. And in order to preface that reaction that I want to talk about, I want to tell you that carbon-carbon double bonds, or things that have carbon-carbon double bonds in them, called olefins or alkenes is another name for them, don't get mixed up. They're pretty stable compounds. Carbon compounds are stable in general. You've got a lot of them in you, of course. And alkanes are in oil. They're very stable, and you can burn them and so on. They don't get mixed up. These double bonds, the blue parts here in this olefin and the red parts, the blue and red don't get mixed up. It's a little political here. They don't form the Republican Democratic one here. They remain in their camps. So that doesn't happen, or at least it wasn't known to happen because there's no pathway for that reaction. There's no mechanism, as we call it. There's no allowed way for that to happen. Except a guy named, as I just mentioned, at DuPont, Herb Eleuterio, in 1956, showed that that was probably not the case. So he took a mixture of these blue and red olefins and found that he did make the mixed one only in the presence of a catalyst. So only when you add a catalyst that allows the mechanism of that reaction to take place, can it happen? It can't happen in the absence of the catalyst. The catalyst is not used up. It over and over does this same reaction, switches the blue and the red parts of olefins. Now, Yves Chauvin, who John mentioned, was the third recipient of the Nobel Prize in 2005, was the one who first wrote down the correct mechanism for that reaction. And that reaction involved, without knowing what else was on the metal, certainly a metal-carbon double bond of an unknown type. All the ones that were known at the time wouldn't do that reaction. And they're called Fischer carbines, who also received a Nobel Prize in '73 with Wilkinson. So he wrote down it has to be some metal-carbon double bonded species, and it has to react to form a ring. And then now you've put a blue and a red carbon together, and you can take that mixed olefin off. You make a new carbene. It goes around again and reacts and produces the mixed species and gets back to the original blue one. So it's a two-step process, 1, 2, of carrying out with time that scrambling reaction. So it was interesting to have just made a new metal-carbon double bonded species of an unknown type. And so I could figure that one out. Maybe I should study that reaction for tantalum, which I did when I went to MIT in 1975. Let me just show you in what we call human terms how that reaction works. So this is always a little fun. So this is, it's kind of like a square dance. So this is the catalyst, the lady in black here, and that's the original carbene, the orange. And here are the blue and red olefins. You can tell they're olefins because they're holding hands like that. And so that's the initial metal-carbon bond. And she goes and she finds either a blue or a red couple, and she found a red couple and forms a ring. So there's the ring. So now she takes her red partner and goes and finds, I think, a blue couple, and you form the mixed olefin here, which she does there. Didn't quite make the ring there, but she does eventually. And that's how the olefins get all mixed up. So you see that most of them are mixed up here. There's still an initial couple there, but that happens all very, very, very rapidly. We're talking about not the speed at which you see it here. It's sometimes in seconds these things happen. So at a very great speed, what we call diffusion control in liquids, the rate at which molecules can just move through liquids. So I spent about 10 years then at MIT really studying tantalum chemistry and figuring out how to make similar kind of compounds that contain molybdenum, that answer to life, the universe, and everything, or tungsten. Actually, tungsten came first and then molybdenum. And they were all of this type in general. The only piece you have to know about really is this metal-carbon double bond. That's the piece that does all the work. There's a T-butyl group as a carbon with 3 methyl groups on it, if you remember. This is called an imido group. You can put various kinds of metal-nitrogen double-bonded species on there. These don't react, these double bonds, only those double bonds. And then what we call alkoxides to change the nature of this species and really allow you to do all kinds of metathesis reactions and get different results. Now, all of these compounds are sensitive to air and water, so you can't work with them out in the air. You have to work under dinitrogen, N2, or argon or some other inert gas. Now, it was Bob Grubbs in 1992, along with Greg Fu. Greg Fu is now my colleague at MIT. He was a postdoc with Bob Grubbs at the time, along with a number of other people who were interested in the possibility that these new compounds that I had made now of molybdenum and tungsten would in fact do this metathesis reaction. I had showed that they would do this reaction. These were discovered in 86, so between 75 and 86 or 87. I worked on tantalum. Then for 10 years, more or less, people studied these compounds. I studied them heavily. And Bob Grubbs was the one who was really had the foresight to see how they could be of use to organic chemists. Now, it's not, for those chemists of you in the audience, if you think about it a little bit, it's not that easy to make a carbon-carbon double bond. It's a lot of work. And most of in fact, all of the reactions are not catalytic. They're stoichiometric, which means you build up a lot of byproducts and you have to dispose of them and so on. The beautiful thing about this reaction is you start with double bonds and you make double bonds. This one you don't care about. That's this 4-carbon piece called butene, and then a carbon-carbon double bond, and you make a ring. It's a very nice, clean, slick way to make carbon-carbon bonds in organic molecules. Pretty simple ones initially. This one, this is a 7-membered ring, I think. Here's a 6-membered ring. Rings. So there are rings that must contain double bonds in what we call the cis configuration. Both of these other bonds, carbon-carbon bonds, on the same side of that double bond. We'll talk about the other configuration later, so-called trans configuration. But this demonstrated that you could make simple organic molecules from simple other molecules having 2 double bonds in them using these metathesis catalysts. So they're clean, fast, no unwanted byproducts, and can't be done simply in any other way. In 1996, so this is really at the end of what I call the second generation catalyst, or first generation catalyst period, between 87 or so and 96 or 97, Amir Hoveda at Boston College here in 95 published another paper, really the first paper that made an even more complicated molecule a natural product. So organic chemists love to make natural products, at least some of them do. And they're always looking for new ways to do that. And these are drugs. They can be lots of things. Usually it's an anti-tumor agent, a drug, or something like that. Often relatively complicated. Many of them have been detected in marine sponges and animals like that. And this is one of them. It's called fluvarucin B1. And he showed that you could take a molecule here, which had a double bond and a double bond, join them together and make a big ring. And now that ring generates this carbon-carbon double bond and makes ethylene. Ethylene is actually a natural product, a gas that goes out of the reaction. And then you elaborate a little further and finally make that fairly complicated molecule. So this is a way he showed that you can do this. And this is now a way that is of interest to many people for making pharmaceuticals and drugs for various diseases. And I'm still involved in fact, trying to do that with the so-called Generation 3 catalysts. So this is really about 1996, the end of the Generation 1 catalysts of that molybdenum and tungsten type that I first mentioned. The second generation catalysts that really are the next 10 years or so are kind of variations of the first generation catalysts. They have these 2 alkoxides joined together by what's called a bidentate ligand, a biphenolate or a binaphthalate, something having phenyl rings in it joined together. And these are like your right hand and left hand. They are chiral. So this one has the S configuration, as we call it, and it is what we say enantiomerically pure. It's like a left-handed catalyst, for example. I held up my right hand, but I meant left-handed catalyst. And so what happens is you can make molecules that then themselves contain carbons that have 4 different things bound to them, and they are themselves enantiomerically pure, one hand, or nearly so. And that's the way most carbons are, many of them, in your body and in nature in general. They're not symmetric. They are asymmetric. And they are, in fact, chiral and often, in nature at least, enantiomerically pure. One configuration about that carbon. So you can take simple compounds like this one, and with this enantiomerically pure catalyst, 5 mole %, it means you can do the reaction 20 times. It's, of course, a rather high percentage for a commercial application, but this just demonstrates that you can do it. And you can upgrade these simple molecules to rather complicated molecules that have one specific structure, greater than 99%, the structure that I show here, in good yield, very cleanly and quickly. So these were catalysts explored between 97 and 2007. And I should mention before I move on that besides organic chemistry, you can make polymers from these metathesis catalysts, because in strained rings like this fancy molecule here, this tricyclic species, you can open up these double bonds and link them together with double carbons in other molecules and make polymers. You can do that twice, and so in this case you make a very highly cross-linked, we say, cross-linked carbon polymer. And this is a very, very tough material. This is made now with a ruthenium-based catalyst that Bob Grubbs has made and studied in the last 15 years, since about the mid-90s or so. So it goes under various names, tellene, meton, and so forth. It's a highly cross-linked polymer that's used for things like automobile fenders and chemical reactors and so forth. And molybdenum, one of my polymers, as I call it, will do the same sort of reaction, making, after hydrogenation of the double bonds in the polymer that is made, a very highly, it's essentially plastic glass. It has glass-like properties, but it's an organic material that you can put on surfaces, dissolve it or melt and put on surfaces. So this is an optical disc coating. They use it for lenses and so forth. That's made by Mitsui now, using one of these well-defined catalysts of molybdenum. Well-defined meaning we know what it is. So initially these catalysts, these metathesis catalysts, were black boxes, and that was really what everybody was interested in finding out starting in the 70s. You know, what was in this box that did this wonderful reaction? We can't play with it because we don't know what it is, so we can't make variations of it. And that's what Grubbs and I did, Grubbs for ruthenium and me for molybdenum and tungsten. This is Bob Grubbs' contribution, one of many variations. Ruthenium is two groups to the right in the periodic table. There's the crucial metal-carbon double bond. It's not as sensitive to air and moisture because as you move to the right in the periodic table, the metal-carbon bonds become less reactive in general, less polar, and so it will tolerate air and water. And that made it very, very useful for organic chemists who didn't want to work in dry boxes or inert atmosphere boxes. They wanted to work out in the air more or less, and they could do that with just maybe a little bit of nitrogen over to flush out the flask, but they could prepare everything on the benchtop. And so huge advances were made then using these ruthenium catalysts because they were relatively insensitive to air and water. But they are different. They're the same. Many of the reactions are the same, but in the end, in the last few years, we've shown that molybdenum and tungsten can really do some remarkable things. So all that led to the Nobel Prize then in 2005. I thought I'd tell you a little bit about Nobel, where he came from. You might not know. He was a Swede. That's no surprise. He was born in 1833. He was a chemical engineer. He was born into a family of chemical engineers. And in that period when he was active, starting around 1860 or so, things were really heating up. It was the Industrial Revolution in many of the civilized parts of the world. And so a lot of things were happening. And so he died in 1896, and he wasn't married, and in his will he left all of his money, and I think it was at that time something like $13 million, which in 1896 was quite a bit of money, to establish the Nobel Foundation and to give it all away in the form of prizes, 5 prizes: physics, chemistry, medicine, literature, and peace. And the way he made his money was to really find a way to tame what we call nitroglycerin. So nitroglycerin, this is glycerin, that's a natural product. You replace these OH groups with ONO2. Those are really NO3 groups. And NO3 is nitrate. It usually explodes, especially if you have a lot of them. And that's what Sobrero had found in 1847, that you could nitrate glycerin and make nitroglycerin, and I know for a fact that it works. I didn't make very much, though, I'll tell you. But he learned it's unstable, and it killed a lot of people. It would explode unpredictably. And he found that if you mixed it, basically made a paste of it with what's called kieselguhr diatomaceous earth, basically a kind of lime skeleton in diatoms in the seafloor, you could make a paste that you could still set off with a blasting cap, but it wasn't unpredictably explosive. So this is called dynamite. This comes from dynamis, the Greek word for power. So this was very important to blasting of rocks and construction and so forth. So he made a lot of money in this discovery, and for other discoveries. He spent most of his time in St. Petersburg, Russia, and he was a Swede, as I said, but he was also fluent in Russian, German, and English, and of course Swedish. So he was a businessman / scientist all of his life. He actually lost a brother in an explosion. He did a lot of work on a lot of research on nitroglycerin itself, and in one huge explosion, his brother was killed along with several other workers. So it took between 1896 and 1901, 5 years to establish the Nobel Foundation and figure out who's going to get the prizes, and he explained all this in a very long will of 1 page, I think it was. So they didn't have much to go by, so this was all new, but they did have $13.5 million, so that's a good place to start. So these are the 5 areas of the original Nobel Prizes. There's a 6th one now in economics, which actually isn't a Nobel Prize. It's a prize from the Swedish bank in honor of Alfred Nobel, established in 1969, but it's usually called the Nobel Prize in Economics. Economics didn't exist in 1896 or around the turn of the century. So here are the first recipients: William Röntgen for X-rays, Van Hoff, you might recognize any students in the audience, physical chemist, von Behring in medicine, and so on. Very often peace prizes go to, the Red Cross has now won 3 peace prizes. So you can win more than 1 prize, and 4 individuals have won more than 1 prize. But it's very uncommon. So there have been about 800 total prizes now given out over the last 110 years. Going to be the end of this year will be the 110th anniversary of the first Nobel Prizes. They weren't given out in every year during the war years. There were obviously some problems. I'm talking about World War II, but it'll be the 110th anniversary in 2011. So the Swedes do the whole thing. So they discuss who they think should get a Nobel Prize, and a lot of people can nominate whoever they want for the Nobel Prize. But it's a percolation process. It takes a long time. Sometimes, in my case, 30 years. So it can take, I think the record short time is like 8 years. But usually between the discovery and the prize, it's 30 years or more. What was I going to say? Forgotten. Here's something important. Interestingly, the records of these deliberations are public only after 51 years. So I'll be long gone before anybody who knows me can read about what happened in the deliberations concerning me and Bob Grubbs and Yves Chauvin. So up to 3 recipients may receive the award in any. It can be 1/3, 1/3, 1/3, or 1/2, 1/4, 1/4. All awards are irreversible, not negotiable. One person has declined a Nobel Prize. That was Jean-Paul Sartre. He thought he was, above Nobel Prizes, so he decided he wouldn't take it. They're only given to living persons. There have been one incident I know of when they were announced, or between the time they were announced, which is early October, and the ceremonies, which is on the anniversary of Nobel's death, it's December 10th, he passed away. So he had the satisfaction of knowing he won a Nobel Prize, but he didn't collect the money. His heirs collected the money. I mentioned here 4 people who have won two Nobel Prizes: Madame Curie, Paul Sanger, Linus Pauling, and a guy named John Bardeen in physics. Sanger and Bardeen are the only 2 who have won their Nobel Prizes in the same area, chemistry and physics. So here we are in 2005. The prize is always, they have a quotation to go with it. This prize was for the development of the metathesis method in organic synthesis. So I've been talking about metathesis, and I've talked about some organic molecules, and that's what the prize was for. I'm not an organic chemist. I'm an inorganic chemist, like President Geoffroy here. I got my prize in another area, I guess, but I do something that is beneficial to another field, like organic chemistry. Bob Grubbs is an organic chemist, and Yves Chauvin is a polymer chemist. He's still alive, but he's retired now. So you really have to do something that's of benefit to mankind, and usually benefits some other area, some other subject area, although there are prizes that are really kind of one-off type things, and they don't seem to have benefited anyone. And there are prizes that are, frankly, probably mistakes, but these are all irreversible. Once it's done, it's done. So here is a picture at the Nobel Foundation. There's Yves Chauvin. One of the recipients is not shown. That's Harold Pinter, who got the prize in literature for, he's a playwright, or was a playwright. He was very ill at the time and has since passed away, so he couldn't make it to the Nobel ceremonies. Here's Bob Grubbs. He's a little bit taller, but he has less hair than I do. And there I am. This is my family. My mother was alive at the time. She was 92. And I asked my brother Ted, who's here on the left. I don't know if you can see that very well. And he's a physician, or was a physician. Surgeon, and I asked him whether it was wise to take my mother to the Nobel ceremonies at age 92, and he said, well, she's determined to go, so that was it. So she went. So there's Ted and his wife, and my brother Luther and his wife, and me and my wife Nancy, that you saw in that early picture of our marriage in 1971, and my mother in the front. My wife's family is a little bit bigger. So she has a sister, Frances, and 3 brothers, Edwin, David, and Johnny here, and their wives. David is unmarried. Here are my 2 sons, Andrew and Eric, and this is Rebecca, who is married to Andrew and was married to Andrew at the time. She's a photographer, an artist, and you can see she's the splashiest of all of us, although all of us look pretty good, frankly, at these ceremonies. So that's what the ceremony looks like in the town hall. It's a big hall, limited capacity, so you can't bring everyone you want to bring. I brought 18 people and paid for their way, and we had a lot of fun. You can't see it probably down here to the right, but I always like to point out that one of these is I think that's my wife's head, and that's one of my sons, and that's my other son. So they're in the second row, and here we are all lined up. Physics people, 3 of them first, and then the 3 of us, 2 medicine and 2 economics people, and then Harold Pinter, who couldn't be there. This is the King Gustav and his wife Sylvia, the king and queen. These are members of the Swedish academies who make these decisions. And these are other Nobel laureates who just happen to be in town. They want to come out and hang out on the stage. And because you do get a full orchestra, and a woman with a wonderful voice is up here. I mean, she's really fabulous. They sing between subjects, physics and chemistry. It's very nice. But it is tense because you have to go out and you have to stand up and you have to go receive the prize from the king. And I'm told that about 225 million people watch this ceremony live. So it's a little, my heart was beating pretty rapidly at this point. So I didn't know if I could do it or not. But I did. And they said, stand up. And so we all stood up. And then you have to go out and receive the prize from the king. He gives you the medal and a diploma and then he sends you the check in the mail. Or actually, they transfer it by, between banks these days. So there's a diploma, all hand illustrated and hand bound, and my wife is a bookbinder conservator, so she really likes this hand done diploma. And there's the medal, 18 karat gold. It's worth a bit, but I keep it in a bank vault. I don't plan on melting it down. So this is one addition to my family now. It was my youngest son's fiancée was Annabelle. She's now a postdoc at MIT in brain chemistry, and Eric and she live in a house they bought about a year ago, this time on his birthday, March 16th, a few days ago. And so that's how we looked on stage after the ceremonies. White tie and tails, all the men running around in white tie and tails for anything, breakfast, you name it. We're out there in white tie and tails. And the women in beautiful gowns, so it's very nice. And then we have a little dinner for 1,300 people, and this is in it was in Symphony Hall was the ceremony. This is the town hall, and so these are where everybody's going to sit, all the guests, and these are where all the king and queen and other laureates and dignitaries are going to sit. And then you walk down this long staircase in order to fill up the central table. And in this year, they started out with the tables kind of bare, and then they brought in flowers and a lot of singing between courses and beautiful a cappella singing in Sweden, which I do very well. It's a lovely event. This is my wife walking with Robin Warren, who was one of the recipients in the Medicine Prize. You can't walk with your spouse or partner. You're paired up by someone on the committee at some point. You make sure that you're not, that you're okay, you're not going to do anything crazy. And then they try to pair you up with somebody who's appropriate. And in my case, that was Princess Madeline. So I hit the jackpot. So this is the youngest of the three children. Princess Madeline was 22 at the time. And it's a little too young for me, but she was definitely beautiful. So that was good. I was worried about stepping on her gown. I was just not being able to find the next step, so I was looking down all the time. I shouldn't have done that, but you can't go back and replay these things. And then this is, of course, now filled with people. I'm somewhere around here, the king and queen in the middle, and people all up and down the table. It's a wonderful, wonderful event. Few photo ops at the end. So these are the chemistry recipients here. Yves Chauvin lost his wife about 2 years before the prize, so he was accompanied by his daughter and King Gustav and Queen Sylvia. So one thing, I'm getting toward the end here, but I wanted to mention that the Nobel Committee said the metathesis method was green. Now, green these days means ecologically not ruinous. That is ecologically appropriate, good for nature and non-polluting. There are various things it can mean. Certainly, it means perhaps the starting materials of a renewable material, not petroleum-based. You might use water as a solvent, not organic solvents. And the products might replace petroleum products. Of course, we're not going to have petroleum eventually, and it's non-polluting perhaps. And so I could see how, in fact, some aspects of what they called green was true of metathesis. It's clean, it's efficient, it's fast, and you can make products now, as we know, from renewable materials. You can make chemicals from renewable materials like seed oils using metathesis methods. I thought I would mention just one of the molecules that, in a family of molecules that is made now by the metathesis process of hundreds, and it's a pheromone. Now, a pheromone is a fairly simple molecule, usually that's given off by insects and other animals in nature, and some people think humans, to attract one another. So there's a pest called the peach tree borer. It's a pest in the larva form, And so, of course, to make larvae, female has to lay eggs, and male and female has to mate, and the male finds the female through the female giving off a little bit of this pheromone. And so the male swims upstream, if you like, and finds the female and mates, and these larvae are produced, and then they infest a tree of various almond and peach and nectarine and other fruit trees, and they ring the tree, and then the tree dies. So it's a big problem in that industry. And of course, the old way to do it would be to just kill everything with DDT, and we know DDT is banned, or some other insecticide. But the smart way to do it is to fool the male. So the smart way to do it is to make the pheromone. So the pheromone of the peach tree borer actually looks like this. Or at least this is part of it. It's actually a mixture of this type of molecule and something where you have, instead of this ester group at the end, it's an alcohol that you can make the ester from. It's a 83 to 17 mixture of these two. But you make this one from two pieces that look like this. The left-hand piece taken twice and the right-hand piece taken twice, and you use a metathesis catalyst to join this piece with that piece. And you make then two of these. And so this comes from petroleum, this comes from vegetable oils, and this is a bona fide process that produces then this pheromone, or it actually duplicates the natural pheromone. And this is then used in very small quantities. So grams, which is about the size of the tip of my little finger here, 1 gram, will cover an acre. So you don't have to put kilograms of material out there, because it's very potent, at least to the male peach tree borer fly, who can smell it at a very low level. And so he becomes very confused, and he can't find a female. So that's it. For mating season, nothing happens. They die, and it's all over, and the peach trees survive. So that's a smart way to really treat a pest problem. I wanted to tell you, just to finish up, I actually lied to you here. I mentioned it earlier that olefins, carbon-carbon double bonds, have two forms. This is called the cis form, where the two, if there are two groups attached as they are here, are on the same side. So there are two protons here, H's, and those two H's and these two carbons, which are actually CH2s, are bound or lie in the same plane. So you can put these two groups on the same side of the double bond, or you can put one on one side and one on the other side. This is called the cis form. This is what's found in nature. And so for a long time, up until about 2 years ago, even after the Nobel Prize, which was given for this method, we could not make selectively the cis form, or called the Z form. Nature could do it, and of course in small rings it had to be the cis form, couldn't make a trans form. But it would be nice to make the cis form, because those are what are present in natural products, such as this pheromone. And recently we've found out how to do that. So this just reiterates what I said. It would be nice to be able to make one of these, the Z form or the cis form, not the other. This is one where they're both on the same side. These are one groups, whatever they might be. And this is one when they're on opposite sides. This one is generally not found in nature very much and is less desirable in organic chemistry. But usually you make about 80% of this one and 20% of this one. So that's not a very good yield of the one you want. So Z is the most valuable in general. Here I show some natural products. This is an anti-tumor agent, motoporamine C. There's a cis double bond. There's a cis double bond in epithylone. We can now make that double bond in 98% yield. Here's something called civitone, which is a fragrance given off by the civet cat. It's present in most perfumes, a large number of them at least. And so cis double bonds are important. And this is now the generation 3 catalyst. You see a lot of things here, but you notice that in addition to the metal, which happens to be tungsten, carbon double bond, and the metal nitrogen double bond, there's another nitrogen-containing group and then an oxygen-containing group. There are 4 different things on the metal. That metal is therefore what we call chiral, just like a carbon with 4 different things on it is chiral. This is a chiral metal center, and we're finding that there are some very special things about chiral metal centers, and I'll talk a lot about this tomorrow, but one of the things that we can do now is to very cleanly take these 2 olefins and join them together to make the cis olefin and ethylene at room temperature with this catalyst. Greater than 99% of the product is this cis product, the one that normally you only get in about 20% yield, and it's a very high yield, 90% or so. This is has come out in a journal we publish in called Organometallics a couple of days ago now, on March 15th, a few days ago. I thought I would mention one other thing, and that's what John alluded to, the importance of fixing nitrogen, reducing it to ammonia. It's done by probably the most important process of the 20th century, the Haber-Bosch process, both of whom got a Nobel Prize. This was the chemist, this was the engineer in perfecting this brute force method of making ammonia from molecular hydrogen and nitrogen at very high temperatures and very high pressures. It's very expensive to build these plants, but they make more than 10 to the 8th tons per year of ammonia this way. Nature also does it on about the same scale at room temperature and pressure, and we have found, as John mentioned in 2003, that a way to do it with molybdenum. Again, molybdenum, the answer to life, the universe, and everything. So it was another achievement that I'm proud of, probably my second achievement. It's not going to win another Nobel Prize, but I've got one. That's fine. I'm happy. I want to just mention 2 things. People don't do work, don't do research without money, like everything else. And these are the 3 foundations that have helped me: National Science Foundation, National Institutes of Health, and the Department of Energy, and a little bit of money from the Army recently have helped me in basic research for carbene chemists, carbene compounds, alkylidines, the application of them to organic chemistry in collaboration with Amir Hoveda, and for polymer chemistry, called ROMP, ring opening metathesis polymerization. I'll talk much more about all these projects tomorrow. I want to finish with just noting what I noted earlier. Here's John Osborne and his wife Karen, my wife Nancy, in 1996 at a restaurant in La Berge de Lille near Strasbourg. It was 4 years before John died of a brain tumor, so I often look at this picture and wish that he were around to enjoy what has happened to me, but maybe he's looking down on us, who knows. So with that, I want to thank you all again, and hope you enjoyed it.
Take some questions.
Yeah, if you want to stick around for a few minutes, I'd be happy to answer some questions.
I have one question. I was wondering if you had any clarification on that experiment that resulted in the fire department coming over.
Yeah, so chemistry sets back when I was 8 years old had good things in them, things like potassium nitrate, charcoal, sulfur, and you mix those up in the right proportion, and you get something called gunpowder, which I did, and it worked. It didn't work very well. It didn't go boom. It wasn't mixed up very well, so it kind of fizzled, and some of it then hopped onto a rug that was in the basement in my lab or near my lab, and pretty soon the rug was kind of fizzling, and it started to burn. And so I had the sense to just gather it all up and throw it out the window. Generated quite a bit of smoke in the house, but nothing really was damaged besides the rug, which was not a special rug. So that's some explanation of what happened when the fire department was called to my house. I think I was about 12 years old at the time. 12-year-olds do that sort of thing, you know. Now's your chance. Yeah. So the question was, do I have any plans for my work in the future? Yeah. These new catalysts that I mentioned right at the end are really unique, since ruthenium, the competition by the fellow called Grubbs, doesn't do these reactions. So we can do reactions that can't be done by any other catalyst. And so we patent these things. I recently started up a company back in December, and I don't really care about making a lot of money. I want somebody to make what I've done useful, and so I thought this was a sensible thing to do. I had the chance to do that, so I've done that. So I don't work for the company. I'm still doing research, but I patent things then at MIT. The company licenses those patents, and so on. So that's what I'm doing in the future. One of the things.
Welcome to the ISU, and have you ever considered that one day you can share your knowledge and take your education out of the American states to the U.S., especially some developing countries like China and India or some any other country? Have you ever considered to share your idea and knowledge?
Well, okay. So the question here is, do I want to share with everybody the secrets that I know, especially in developing countries? I try the best that I can to do that. I travel and give lectures, but I don't have any great secrets. I'm not, I'm not a deity here. I've done some good things, and I explain, what I've done, and try to give you some idea of what it takes to do that. But I can't give you a recipe for how you can do it, or how any one person can do it, and I don't know what special combination of talents I have. It just happens that I have some combination that's the right combination. So I can't really give you the answer. I try, but I can't give you the answer. Yeah, so times I was discouraged in my research. Well, when the house was almost burning down, I was kind of discouraged. We all have times that we're discouraged, but one thing that it does take to become successful is to not let that deter you. In fact, sometimes I think scientists feel like they get stronger when they meet some resistance, and sure, they're discouraged, but they go out and have some wine or something, and the next day they're fine, and they're back in the lab, and they're gonna fix the problem. So I can't think of any particular gigantic discouragement that I had. Just a lot of little ones, sure. Almost every day, discouraged in some way, but usually it's a fairly small thing, and you can work through it. So I didn't have any big problem, but a lot of them, if you add them all up, sure. That's what we do. We try to come back, beat Mother Nature somehow. But she's tough, very tough. Any advice that I wish I had been given by a mentor? Well, I was given a lot of advice by John Osborne and my postdoctoral supervisor, Lord Lewis now, and by George Parshall, my group leader. And George Parshall said, "You should leave DuPont." He said, he knew that I wasn't going to be a lifer at DuPont, I guess is what he was saying. He didn't tell me to get out. He said, maybe you really should go find an academic job. So that's what I did. So I've been thankful for all that advice. I can't say there's any advice that was not given to me that I wish I had, except maybe to answer to life and the universe and everything, but I learned that myself. So eventually, molybdenum. So tungsten's pretty good too. And tantalum was my first love, so that's, I can't, they're all nice. But no, I can't say there was any specific advice that I wish I had been told.
How much time do you spend in the lab? And how do you divide time between teaching, lab, and what's the longest on something?
So the answer is how much time do I spend in the lab? How do I divide it? And what's the longest time I've spent on something, right? Oh, you mean one, just a marathon in the lab? Well, let me start. Right now, I don't go in the lab. I'm prevented from going in the lab to do anything because my students can't stand it. You know, it's just, I'm not, in fact, whenever I do something, I do go in the lab. They all gather around. They think it's really amazing that I can actually do something. So, so I don't myself work in the lab anymore. But I'm in the lab talking to them all the time. Well, in my creative period, I like to think I'm still creative, but you know, when I was a graduate student, I would work long hours. In fact, there you see, my PhD supervisor would kind of open the door and throw in a sandwich and close the door. Because he knew I needed some food, you know, because that was the main problem. I hadn't eaten for like 12 hours. So I guess the longest period of time, yeah, some long days, 12, 14 hours, 16 hours. I don't know. I never did all-nighters, as I recall, except to study, because you don't want to do that if you're in the lab. It's not good because you do lose concentration and so forth, and you have accidents, so that's not good. How do I divide my time? Well, right now, it's more complicated. I don't go in the lab, as I said, except to talk to students, but I spend as much time as I can talking to them when I'm there to help them out. I only have 5 students now, about 7 postdocs, so I'm no longer taking students, because that's a 5-year commitment if you take students before you retire, if you retire. And so I'm doing what's called switching to postdocs. So I don't take students. Well, I have a family, and you saw them, and so I had to balance a lot of balls, but it is possible. And all you young people out there, I want you to know that it is possible to balance all those balls. It's difficult from time to time, but it can be done. Okay. So give it to me again. What? Yeah, that's a good question. You don't have to start when you're 8. I just so happened I did, but some people who've won Nobel Prizes didn't get interested in their subject till they were like 27. You know, they were in graduate school. They're quite a number. I mean, I can think of 1 or 2, but I think there are quite a few. So you don't have to become interested in your lifelong work when you're young to actually be successful at it. Very successful. So, yeah, that's the answer. You can start late. You can be a late bloomer, okay, as we say.
So you pondered the exchange of old and now, and so what would you think the new frontier as far as a new discovery to make be the solution to life, or possibly another solution that's not molybdenum?
Yeah, so what's the goal now? Well, I show you how to make Z double bonds. That's nice. We want to make selectively E double bonds. And then if you come to my talk tomorrow, I'll show you how you can put those to use. and completely control the double bond chemistry, because making and manipulating double bonds in organic chemistry, believe it or not, is in a relatively primitive state. If you think about it, there's some reactions that work, but none of them selective and none of them catalytic, really. So there are double bonds everywhere. You're full of double bonds, believe it or not, and so it's going to continue. I don't think any other metals than the ones we know about, molybdenum and tungsten and ruthenium, are going to be successful for various reasons. I could go through the list, but it's true that people have tried other metals, tantalum that I tried in the beginning. It'll do this reaction, but it's very reluctant to do the reaction. Other things happen and the catalyst decomposes. So that's generally what you're fighting. These metal-carbon double bonds are natural products, so you've got to remake them. That's the whole idea. It becomes a catalytic process. You use it over and over and over and over again. If it decomposes at some point, then that's it. And that's what happens for virtually all other metals. There are other reactions that set in and don't allow that reaction to proceed. So the future is more of what I've just shown you, and you can hear about tomorrow in great detail if you like.
If I understand your timeline correctly, you made these metal-carbon complexes first before Chauvin found they were responsible for olefin catalysis. What direction were you planning to go when you started?
Yeah, that's a good question. So what was I doing making tantalum compounds, metal-carbon single bonds, right? I was just having fun. I thought, and that's what scientists often do. I mean, they have a goal, but they do things because they're learning, it's new, they can publish papers, and maybe they'll make a discovery, like I did. I was fortunate. So, yeah, I had my reason for making metal-carbon double bonds, tantalum carbon, metal-carbon single bonds, tantalum carbon single bonds, and that was to make another polymerization catalyst. But, if you knew you were going to make a discovery, you could make lots of discoveries because you could predict what you're going to do, but you can't. So you have to be doing something else in the process, and that was my excuse.
Well, I apologize for cutting this off. It's very animated and very interesting to hear you people ask these questions. However, first of all, I would invite you to come to his seminar tomorrow, which is at 4:10 in the Lecture Hall 1352 at 4:10, and he'll tell you more about this. And I'd also invite you to an hour tomorrow afternoon from 1:15 to 2:15 in room 1651, where Professor Schrock will be happy to talk with you and discuss career plans, research plans, etc. And if all of you come, we'll find an auditorium where we can meet. So now there are some refreshments over there at the table, and Professor Schrock will be here a few minutes yet, and you might be able to buttonhole him before he leaves.
Yeah, I'm not going anywhere. I'm here.
Thank you very much.